Hello, everyone. My name is Xingling and I'm from University, UK. And before I start today's topic, I want to thank for my co-authors and my supervisors. And today I want to talk about the damage-based initiation and growth of cracks in CGI, compacted graphite iron. And today I may compare the experiment data, not focus on the experiment data. So first of all, why cast iron? Because cast iron is widely used now in the automation industry, and it has very good thermal and high strength durability and excellent machinability, and also good sound and vibration damping, and also it's relatively cheap compared to another composite or metal. And here now is the microstructure of CGI, and you can see we named 3 different types of graphite here. And the circular one, we call it the larger graphite. And if the shape of the graphite particle is very flake, and we call it the flake graphite. And it's intermediate between the larger and the flake one, and we call it the vermicular graphite here. And now there are current some models about the cast iron. The first one is very popular one is directly incorporation of microstructure into the FEM model, use the image process. You can see from here, they will generate the realistic microstructure here. And also there are some people, they use the RVE model, like the simplified graphite models. And also they will discuss the Perlite model, and they all think the graphite nodular model as a rigid particle. However, there are some people think the modeling of graphite as a primary voice. So there are some discussion about that. And now let's talk about the research approach. So this is our in situ tensile test specimen, and you see it's very thick. It's only 0.5 millimeter. So, and first of all, we put it into the EDM machine to cut from the cast iron bar, and then they mount it for a better polishing, and then we polish this one. And after that, we put that into the SEM, and then finally we got the micro cracks of our CGI. And here's a microstructure characterization, and we use optical softwares, dynamics explicit method, and the domain is here, and the volume fraction is assumed 8, and the mesh size is the best we find is 10 micron, and yeah, the loading is tensile. The boundary condition is periodical boundary condition here. And this is the SEM micrograph we got from this the experiment, and then we use SolidWorks to import the real microstructure, or we use image to get the simplified microstructure, and then we compare this one. And there are 3 different, because we compare the strategy of different damage models. So we use 3 different constitutive law, and the first one is ductile damage, and I don't want to waste a lot of time here. And then second law, we use the cohesive law, cohesive real element, and this is a parameter which I use in my modeling. So in my model 2, there are cohesive insert into the matrix and the interface and the graphite, and to generate the quark propagation. And the matrix properties here. And also we use the constitutive law of Johnson-Cook, and it's a very famous model too. And this is a parameter I used in my modeling, and the graphite particles parameters here. And yeah, and let's go to the experiment-based validation. So first of all, we captured our sample with quark in like this one, and then we build some model, and then we find the risk concentration is very same, in a good agreement with the experiment part, and also for the simplified one. And there are some stress concentration near this part, but however the most part of the stress concentration is located from located on the right. And the stress concentration mainly appeared between like the two vermicular graphite and the distance here, and also like this one. And this is engineering stress strain curve for the real model with PBC and the simplified with PBC compared to others tensile test. And it's in a relative good agreement with the experiment one. And then after that, we do the tensile test here, and it's slightly different with another people's experiment because the thickness is only 0.5 millimeters to better capture the quark propagation. Because here, first of all, we want to know when the strain is 0.5% of here, and the stress is around 200, and then we find no crack at all. However, when the strain around the 1%, we find some small cracks here, and also the crack coalescence into this part. And after the final debonding, and we find some interface debonding and also some small cracks here. So we got the fracture strain in my modeling, so which will be used to validate our models. And then let's talk about the result. And there's the first two are modeled without PBC, and then the second two are with PBC. And we find no PBC, the stress will concentration will only appear here. And however, for the PBC, the stress concentration room will be higher. And then if you compare model A and C, and then you find the PBC will not affect the graphite degradation level. Degradation level means the percentage of the graphite element will be delayed from our model. And also compare B and D, B and D, so A and C. However, after we improve the PBC, we find our strain at quark initiation increased, which will be and also we found these two curves are not good agreement with the experiment. However, with PBC, the strain at quark initiation will be more close to the experiment. So the following, we use the simplified one, and then the first one is without the first one is any ductile damage into the graphite, and then the elastic and plastic behaviors for the matrix. However, for the second one, we use cohesive into the this one is Johnson-Cook for the matrix, and also ductile damage into the graphite. For the third one, we use the cohesive into the graphite and the matrix, and also for the interface. And for the model 4, we use Johnson-Cook damage model into the matrix and cohesive interface near the between the interface between the graphite particles, and also ductile damage for the modeling. And then we compare our predict quark path with the experiment part, and we find the upper part is in good agreements with experiment. However, this part is slightly differentiated. This is mad because we use the simplified model. It will have more accuracy. However, the prediction of the quark path will slightly decrease. And then for the model 1 and model 2, we find it's more close to the experiment. However, for the model 3 and model 4, the engineering stress strain curve is drop. So we compare the model 2, model 3, model 4, and we find the model 2, the quark initiation strain 0.6, which is in good agreement with our experiment here. And also for these three, the first matrix quarking should be around 1% of the string. However, it's slightly different. However, this model 2 is still the best among the model 3 and model 4. So we make a comparison about all 4 models, and we find this one with median computational cost. However, the quality to fit the experiment data is higher, and the prediction of the quark path is higher. So we would recommend use Johnson-Cook damage model into matrix and the ductile damage model in the graphite for our modeling. And then after that, we discussed the effect of graphite particle spacing. What this means is like because the graphite particle, we can calculate the distance between each particles. So, and the L4 is average distance for the 4 labors, and Ln means the nearest labor distance. And then the third and the fourth variable parameter are the normalized parameter here. And after we consider the size effect. So here, first of all, we find all the quark will initiate between when the distance between 20 or to 45, and if it's longer, the particle is less likely to affect the graphite particles, and each dot means when this graphite debonding, and then we got when will this graphite debonding into my model. And also, if we compare figure A and figure B, we find this indicates with the increase of the displacement distance between the graphite particle, the quark will initiate earlier, which is wrong, because if two graphite particles close to each other, the stress concentration will be more pronounced in realistic part. So we need to consider the size effect of graphite particle. So we normalize our result with a size effect, and then we can say now this model 1 here, it's more close to the realistic one, because with the increase of the distance, and the 2 graphites are located far away from, and which is less likely the quark will initiate, and less likely it will affect each other. And also we find also it's the same for the model 1 and model 2. It's the quark will initiate around 0.6 to 0.8, which is in a good agreement with the experiment. However, for the model 3 and the model 4, the quark initiate earlier than what we have observed in the experiment. So this is slightly let's come to the conclusion part. So conclusion part, first of all, the Johnson-Cook damage model require relative low cost computational cost, however, provide a strong fit to the experiment along with a very good predictability for the quark initiation and propagation. And the cohesive model demonstrates the good quark propagation prediction. However, it's exhibit bad fit with the experiment engineering stress strain curve and high computational cost. And the PBC will have a better material experiment when we use, and the quark consistent initiate at the tip of the 1 micro graphite. And the closer distance between those tips, the more pronounced the stress concentration became. And the last is, when we consider the size effect of the graphite particle, it's very important for the adequate analysis of the fracture behaviors of the materials. Thank you so much for listening.